Good evening, students. Am I audible to everyone? So, how was your 3 days break? Yeah, it's good to have a little break in the time, right? When you are doing studies and all of a sudden you get a break, it feels good. Okay. So, you tried those two questions, right? Hmm. So, first question was to calculate what the rate of diffusion of air in a mixture of water and ethanol. So, what is the answer that you people got? In kilomole per meter square per second. What is value of Na? No. Wrong. Anyone else? Did anyone else try? Mr. Amal? Yeah. Swati? So, tell me the answer that you people got. Mole per second per meter square. No, it's wrong. It's wrong. Yeah, your units are also in mole per second per meter square, right? Let other students also come. Then I'll explain the answer to you. So, Swati, you didn't try it out, or you weren't able to solve it. You should have tried here. See, when I ask you people to do a question, I think you should do it because it's for your own benefit. Okay? Don't worry. In the future, keep it in mind that whatever the question is given to you for the homework, you need to do it. Okay? Okay, let's start the question. Let others people watched all lecture yesterday. Yeah, you should have watched it day before yesterday. Even if it was yesterday, still you should be able to do the question. You should have tried at night or see. It's up to you. You had today's holiday also. Okay. So, anyways, it's not a big deal. I'll tell you how to do the solution. But before that, let's recap the concept of multi-component diffusion. See, I still don't know. So it's on this side itself. Lectures must have got uploaded, Right, Swati? It was on the site itself. Yeah, you can see whatever it is. See, I'm not concerned with these kind of things, technical things. I'm concerned only with teaching, so I don't know where you get the lectures and how you can calculate it, how you get it. Okay, just ask, either you can either contact in the office any for any problem, or you can ask with each other. Okay. Yeah, yeah, sure, sure. See, I really have no idea where it gets uploaded and where you can get it. But I know that the lectures, whatever delivered in the classroom, in the online classroom, they are all recorded and then uploaded somewhere so that they can be accessed again. Okay? Just have that knowledge where it you can get it from. Okay. So before starting this question, I'll tell you again the concept of multi-component diffusion. Let this is a mixture of A, this is A. Oh, okay, and B, green color. We might face some technical problem today also because it's going on its own. I'm not doing it. Okay. See, let this is our green B, and this is our A. Okay, and a component, let's say C or X. Let's say C. It wants to go inside it. It will go through it. So this C, when it will go through this mixture, it will interact with these A particles and with these B particles individually. Okay. So how is the effective diffusivity calculated in this system? We calculate the diffusivity of C with respect to A and with respect to B. That is dCA dCB. Okay. That is the diffusivity of C in a mixture of C and A or through a pure A, plus and individually the diffusivity of C through pure B. Okay, these two are calculated individually and then the overall diffusivity is calculated. Okay, now how the values that we got are used to calculate the total diffusivity of C. See, total diffusivity of C is equal to YA upon dCA plus YB upon dCB. Okay, this is the formula for calculating the effective diffusivity of C in a mixture. Now YA is what? YA is equal to mole fraction of A in the mixture of A and B, because this is a mixture. C is a foreign substance, so we'll take it only the mixture through which the passing is going on, not including the C. That is, it is equal to Na upon Na plus Nb. It doesn't include C. Similarly, Yb is again Nb upon Na plus NB. It doesn't include C. Got it? So this was taught to you people, right? Any problem in that? Yeah, exactly. Now see, this is the concept which I mentioned you, and using this concept, this question was to be solved. The question that Ahmed and Abhay did, they did what? They took YA, that is the mole fraction of A, including C. Similarly, YB including C. Okay, that's why the answer was coming wrong. First, you need to remove air from the mixture, then the remaining two compounds, that is water and ethanol. Okay, in that mixture, you need to calculate YA and YB individually, and then you need to calculate the effective diffusivity from those mole fractions. Got it? Okay, everyone got it? Mr. Ahmed, any question? Yeah, exactly. Taking 1 mole as the basis, then you can calculate the mole fractions in the mixture. See, initially it will be 1 mole, but after removal of air, it will get reduced total number of moles. Then out of those total number of moles, you need to calculate the mole fractions of water and ethanol separately. Okay, so try it out again tomorrow. I have mentioned you the concept. Okay, if tomorrow you are not able to do it, then I'll do the whole solution here. I think you will be able to do it because it was the only thing that was creating problem in getting the correct answer. Okay, but for your calculations, I'll tell you the answer. The answer is Na is equal to 1.75 into 10 raised to the power minus 4 kilomole per meter square per second. Okay, this is the answer. So try it out on again tomorrow. Okay, so I think you will get the answer. Hmm. Now the second question regarding the curves. Did you find out the best possible explanation for the curves? For the two-phase region in distillation as well as the adsorption of a highly soluble gas or absorption of a high soluble gas. just give me some reply. Did you find out the explanations for the curves that I made on Friday? Yes. Yeah. Okay. So the expression is the analytical explanation which confirms that the curves are right. But what about the physical significance? How did you describe it physically? Like that of distillation, in which the XA is greater than XAI, but the YAI is much greater than YA. Why? And why did I put it in the upside, not below it? See, everything is there for a reason, right? You just can't simply put something up and down. So, did you think about the possible explanation? Yeah, that is the two film theory. That explains that there will be a curve either increasing or decreasing inside the interface. That's the thing. Okay, but the explanation why curve, that is for the curve for the vapor phase is upside and the curve for the liquid phase is below it. Come on, give me some answers, yeah. You must have done some homework. At least try to please me so that I can think that yes, my students are doing good. When given a question, at least they have tried to their best. No, nobody got any answer for me. Yeah, exactly. See, in the distillation, the amount of vapors or the mole fraction of more volatile component is more in the vapor phase. Okay, so it means that if A is the more volatile component that is being distilled, it will have a higher composition in the vapor phase. See, XD is always greater than XW. It can never be less or equal to XF or XW. It is always greater than that. It means the vapor phase composition will be more than that. And the second thing, that is the curve, like XA was more and XA was less, because the mass transfer can occur only in the region of decrease of concentration. That is, when there is a concentration difference, then only mass transfer occurs from a region of higher concentration to a region of lower concentration. It means for the component to move from bulk through the interface, it should have a concentration difference, okay, which explains why the X curve, like this was the intermediate. क्या हो रहा है यार ये अपने आप पे यहाँ पे क्लिक कर रहा हूँ अपने आप लाइन खींच ये वही था अभी दो जगह हो चुकी है नया पेज ही है okay. It was like this. Right or not? Yeah. It means this is liquid bulk. Now, in order for molecule to move from bulk to interface, there had to be a concentration difference. Okay. So that's why XA was more and XA was less. Now, we know that alpha is equal to y upon 1 minus y upon x upon 1 minus x. On rearranging, y is equal to alpha x upon 1 plus alpha minus 1 into x. Since alpha is always greater than 1 and usually greater than 2, so it will be always greater than x. Okay, so equilibrium relationship, it will give what? It will transfer to a higher phase region, that is YAI, and then from here to here, this is the bulk, and so on. Okay, now YA star was, यार देखना क्या हो रहा है यार क्लिक कर रहा हूँ अपने आप ही कैसे okay. This is YA star is greater than YAI. How? Because YA star is greater than YAI because in the distillation, see, we are facing some technical problem. I'll try to fix it. Okay. Yeah, alpha is the relative volatility. I'll teach you in the distillation itself. Okay. Here in the distillation, this is the 45-degree curve, that is the diagonal, and this is equilibrium curve. And we take the values here, and this is how. So these are the operating lines. Okay, this is equilibrium curve. The operating line touches the equilibrium curve only in a special case. Otherwise, in all other cases, equilibrium value is always greater than operating value. So that's why YA star is above YAI. Okay, got it? Everyone? Yeah. This is the explanation that I was expecting from you people, but none of you did it. Yeah, that's not right here. See, this was the first question that I gave you for the homework. You should have done it in a better way. Okay, no problem. Now on that day, I stopped from telling you the empirical relations because that would have taken our time, and I wanted to do the theories. So today, now I'll just, yeah, the similar reasons for absorption also. I didn't tell you absorption right now because we are going to start absorption in a short while after the humidification. That the next chapter is humidification and drying, and then we will do absorption and stripping. So there you will get the curves, okay, the possible explanation. And since absorption is not known to everyone, but distillation everybody remembers, whosoever done the chemical engineering mass transfer. So they can at least remember the distillation, okay. So that's why I mentioned the curve. I explained it using the example of distillation. So now the turbulent the empirical relations. I mentioned for laminar flow inside a pipe, right? That is Sherwood number was equal to, yeah, 3.66 for flow inside pipe. Number one, a laminar flow. See, try to see on the board at the moment itself because I'm facing some technical problem. Okay, these lines are getting drawn on themselves. So at least try to focus on the words that I'm writing. Okay. Number one, if we have the case of constant wall concentration, Sherwood number is equal to 3.66. Similarly, if we have the case of constant molar flux, the value of Sherwood number is equal to 4.34. Okay. Now for the turbulent flow. For turbulent flow, Sherwood number is equal to 0.023 into Reynolds number raised to the power 0.83, Schmidt number raised to the power 0.33. Okay, so this is for the Schmidt number between 0.6 to 3000. Okay, now in considering the viscosity effects also, it will become, okay, these are all empirical relations which you need to remember. Okay, this is for flow inside the pipe. Now we'll do the case of flow over flat plate parallel to the surface. Now for this is again boundary layer theory. For laminar, Sherwood number is equal to 0.664. Reynolds number raised to the power 1 by 2. Schmidt number raised to the power 1 by 3. Okay. For turbulent flow, okay, for it Reynolds number is less than 10 raised to the power 5. There it was 2100 for pipe, but for a flat plate it is 10 raised to the power 5. Okay. 0.036. Reynolds number raised to the power 0.8. Schmidt number raised to the power again 0.33. When RE is greater than 10 raised to the, or RE has a range of, okay, it is 10 raised to the power 4. Yeah, not 5. 1, 2, 3, 4. Yeah, 10 raised to the power 4 is less than equal to 3, 1, 2, 3, 4, 5. Okay, these are all empirical relations. Next, for the flow past single sphere. There are various across the cylinder, whether it's going perpendicular or parallel. Similarly, for the plate, when it's going perpendicular. But those relations are rarely asked because these are not the common examples. I'll tell you only the three examples. That is the flow inside a pipe, which is very common. Then flow parallel to the surface, that is over a flat plate. And the third one is the flow past single sphere. Because these three cases are asked most frequently. All others, if asked, even in these cases also, even if they are given, they are asked questions about it, they will tell you the relationship. So you need not worry about it, but at least you should have an idea of the relationship because these relations might be asked in interviews. Okay, so that's why I'm telling you the some relations for you people in order so that you might at least remember what kind of formula was there. Okay, for this Sherwood number is equal to 2 when Reynolds number is less than 0.1 or Reynolds number is less than 1. C, that is creeping flow. In some textbooks, the value of Reynolds number in order to have a creeping flow is given as 0.1, and in some textbooks it's given as less than 1. So you can take any. I think 0.1 will be much better because it's on the safe side. Okay, then Sherwood number is equal to 2 plus 0.6 1 by 2 1 1 by 3 when Reynolds number is between 2 to 1000, that is it is in laminar flow. Then similarly for the turbulent flow, Sherwood number is equal to, this is for laminar, okay, Sherwood number is equal to 0.35, Reynolds number raised to the power 0.6, Schmidt number raised to the power 0.33. When Reynolds number is greater than 2000. Okay, what is creeping flow? Uh, do you understand Hindi, Swati? या तो टर्बुलेंट मतलब कि तेज, लैमिनार मतलब कि धीमा, और क्रिपिंग मतलब कि रेंगने वाला. Okay, when the fluid moves so slow that we assumes that it's not even moving. Okay, it's equivalent that it was not moving, so that is called the creeping flow. Okay, so this it will be discussed in detail in fluid mechanics. These all flows will be discussed in detail in fluid mechanics. Don't worry about it. Okay. Yeah, constant wall concentration. Similar to that, constant wall temperature for heat transfer. Suppose you have a transferring wall or the wall with um, opening for the compound to diffuse inside it. Okay, or you can assume that a constant rate of diffusion is occurring over there, like it's a porous medium. Okay, so in those all cases it's a case of constant wall concentration. Yeah, these are all the experimental values, so we just need to remember them. The derivation for the constant heat flux and the constant wall temperature for the laminar flow in a pipe will be discussed in heat transfer. So these are the analogies that we have taken from heat transfer and fluid mechanics. Okay, so you need not worry about them. They will be discussed individually in detail in individual subjects. Okay, because see, if I'll explain each and every derivation over here, then it will take a lot of time to do the mass transfer, and in fact from the mass transfer point of view, these are not so important. You just need to know that if a question is asked, then you are able to take the analogy from other subjects also. Okay, so we did some questions. Let's do one more question. Yeah, don't worry, Sunny. See, if you are sick, then obviously you should take rest and then attend the, or you can watch the videos later on. Okay? Yeah, no problem about that. See, the lectures are uploaded. Okay, bye. Good night. Okay. Uh, on Friday, we did some questions. So, did we do question of GATE 2014? That is a spherical ball of benzoic acid. Did we do it? I think we didn't do it. So let's do the question. Okay. Let me tell you the page number where it is given. Spherical ball of benzoic acid. It is given on the. We did it. Yeah, 1.5 centimeter. We did it, right? Okay, okay. Then that's pretty good. Okay, okay. Yeah, got it. Um. Okay. So we did the questions. Now we'll go for next chapter. See, I didn't remember that whether we did the question or not. So don't mention it. It's pretty good that we did the question because now we can move ahead to our questions. Just have okay. The next chapter is drying and humidification. What is drying? What is drying? Everyone tell me what is drying. भाई ये नहीं करने दे रहा काम. No, not extraction of water from molecule, not from a mixture. Yeah, I'm facing some technical problems. Yeah, removal of water from where? From where are you removing water? Exactly. Okay. So let me write the definition. Drying is the process of removal of liquids such as water, benzoic acid, etc. It can be anything, etc. from process material that is solid. Okay. Generally, we take it water. Okay. So, or in general terms, it is generally referred to as the process of removal of small amount of water from from a moist solid, that is the solid containing moisture. Okay, so this is drying, while evaporation is the term used for removing a relatively large amount of water. Understood? What is drying and how it is different from evaporation. Okay, let's say for example, you dry your clothes, you don't evaporate your clothes, you evaporate water from other substances. Okay, now the next thing, what is humidification? Humidification means to indulge or introduce moisture into air. Humidification drying is done for solids in our engineering, and humidification is done for air or gases. Okay, any question? Yeah, okay. What are the different types of drying? I don't know how these lines are creating on themselves. On the basis of mode of operation, It can be either a batch drying or continuous drying. Okay. Second, on the basis of physical conditions. It can be at atmospheric conditions, drying by hot air. Second, vacuum drying with indirect heating. And third one is the freeze drying. Okay, in which water sublimes from frozen material. You have seen all these things. That is, the freeze drying is used in hilly areas, that is cold areas such as Shimla or Jammu Kashmir, to preserve the foodstuffs. Okay, there in the streets usually you will find out. Anyone from Jammu Kashmir? Anyone of you is from Jammu Kashmir or from any hill area? Am I audible to everyone? So, is any one of you from Jammu Kashmir or any other hilly area? Okay, so probably you don't know about it. Okay, see, even in the news or in those areas, what is done that you can't grow crops the whole year. See, like in my region, that is, I'm from Haryana, and then in that region, you can grow the crops for the whole year because the conditions are available for doing the farming, because availability of water is there, electricity is also present there. In fact, apart from that, the atmospheric conditions are well suited for the crops also. But in the very cold regions such as Jammu Kashmir or in the upper parts of Shimla, in those areas only in summers can you do the farming. So during the summers, those people do the farming. They grow the crops such as vegetables and all those things, and then a fraction of that is consumed at that time, like we do today, the fresh things that we eat. The remaining, the major part of the vegetable crops are freeze dried. Okay, they dry it using the freezing method and they preserve it then. Okay, so in the winters you will find out that even simple vegetables like brinjal and all that, they will be in the smaller in size and little dried up. Okay, so when we do the freeze drying, then what happens, then the surface gets a little bit shrunk. It retain only a small amount of moisture, so the possibility of that food stuff to get um, rotten becomes less. Okay, so this is how it is done. Okay, atmospheric drying, you all know, that is the drying of clothes at your home during any season. And the vacuum drying is a special kind of drying in which we apply the vacuum conditions to remove the water. Okay. Any question? Yeah. Okay. So, humidification. Humidification means what? The transfer of moisture from a liquid to gas, that is air. Okay, the air get humidified when it rains. The humidity increases. You must have felt even the change in the atmosphere when it's raining. See, before rain, in summers, the air feels a little bit dry. Okay, but after it rains, it becomes a little bit different. Okay, because there is a high humidity inside it. And that is because the water has been suspended inside the air. Okay, then dehumidification means to remove the water from air. Okay, these are the general definitions. Let me write it down. What is happening here? That is the transfer of water. Usually water is taken, not any organic substance, but if even if it's taken as organic substance, that will be the same case. Similar to that, the difference between the transfer of organic substance or the transfer of water, I'll tell you using the humidification chart. Okay, from the liquid state to the gaseous mixture of air and water. Air and water vapor. Okay, so dehumidification. D means opposite to that of humidification. Okay, so it is the reverse of humidification, and the vapor is transferred from gaseous mixture to the liquid state. Okay, now just tell me the difference between boiling and evaporation. First, tell me what is boiling. Everyone, think about it, because since I have asked, there must be a difference between those two. Okay, so think about it. What is boiling? How it occurs? How is it different from evaporation? Okay, just think about it and just tell me. Swati, you're wrong. No. It can occur at 100 degrees centigrade for water at 1 atmospheric conditions. It can occur below 100 degrees centigrade at um, vacuum conditions. It can occur greater than 100 degrees centigrade at higher pressures. Think about it. There are some differences. Just think about it. Yeah, the evaporation occurs on the surface. Anything else? So doesn't that happens in evaporation also? Yeah, evaporation is surface phenomena, but bulk boiling is bulk phenomena. That is right. Anything else? Nothing. Okay. So you are going a little bit ahead. No, that's not a problem. Also, the vapor can change even more vaporized. No, I don't think that it will get superheated. Okay, every one of you tried to your best, but I'll tell you. Let me write the definition. I think that will explain everything to you. The partial pressure and vapor pressure concept comes when there is a mixture. When there is a pure substance like water, a pure water, then there is no concept of partial pressure. At that point, the two terms, that is partial pressure and vapor pressure, are same. Okay. So here I'm considering only the water, right? So you shouldn't worry about that. Yeah, when we'll do the mixture, then obviously the pressure of the partial pressure of a component will be less than the vapor pressure for an ideal mixture, even for the most of the real mixture. But it will be equal to the vapor pressure for isotropic mixtures. I'll tell these concepts to you when we'll do the distillation. Okay, so let's write down the definition of boiling. It is the bulk phenomena. Okay, the bulk phenomena in which rapid vaporization. Vaporization means the phase change from liquid to gaseous state or vapor state of liquid occurs. It is possible when the liquid is heated in such a way that the vapor pressure of liquid is equal to becomes equal to that of total pressure above fluid surface. Yeah, look at the definition and tell me, did you understand it or not? I have mentioned that the vapor pressure of the liquid should be equal to the total pressure above fluid surface. So this is a very um, important concept for boiling. If this condition is not met, then boiling can't be achieved. Got it? Yeah. Equilibrium, we can't really say that it has reached equilibrium. I'll tell you when the condition of equilibrium is achieved. Okay? See, if the molecules are moving from liquid phase to the gaseous phase, how can you say that equilibrium has been attained? Equilibrium can also only be attained when the number of molecules that are moving from liquid state to the gaseous state is equal to the number of molecules moving from gaseous state to the liquid state. Right? That is called the equilibrium, na? The amount that is going is equal to the amount that is coming back. Yeah. So if there is a driving force, that means the equilibrium has not been attained. That is the main concept for mass transfer, na? Everything tends to go to equilibrium. That's why mass transfer or any uh, spontaneous process occurs in order to attain the equilibrium. Any question? Yeah. Shall we go for the next? That is evaporation. Now, what is evaporation? Oh shit. Uh, Whiteboard. Okay. No, it's okay. Yeah, evaporation. First, I'll write down the definition. Then, obviously, we'll understand everything from it. Okay. The surface phenomena in which vaporization of the liquid occurs yeah, it can be related to it. We'll get to that in thermodynamics, don't worry about that. See, a subject is not a subject on its own. So when we are dealing with the phenomena of the real life scenario, then we need to apply more than one subjects. But while studying, I'll tell you only one subject related problems. Then the aspect of other subject will be taught in the other subject. Like in the heat, see if we are boiling it, then obviously transfer is occurring inside it. So we can apply the process of heat transfer inside it. Since due to evaporation, its viscosity will change. So obviously its inert thermal will also change if it's moving. So we can apply the fluid mechanics to it. Then the concentration difference results in the form in the what the movement of molecules from bulk liquid to the gaseous phase. So we applied the mass transfer. Then on attainment of equilibrium, we'll apply the thermodynamics. Okay, so these are all the relations that can happen. Okay, any problem can be correlated to any other subject also. So for the time being, when we are doing the mass transfer, let's focus only on the mass transfer aspect. When we'll do the next subject, then you will know about the other aspects, and on completion of the whole curriculum or the whole syllabus, then you will get to know the each and every aspect of everything. Okay, let's get a little dose of everything in the different scenarios. So so evaporation is a surface phenomena in which vaporization of the liquid occurs due to concentration difference. Okay, it continues until equilibrium is achieved between the molecules leaving from the surface and returning to it. Okay, now look at the definition. Any questions? Yeah, so now you got the difference between evaporation and boiling, right? So the next question for you people is, what is the difference between a gas and vapor? See, before doing humidification and drying and all that, you should know all these concepts. Okay, but before going for the gas and vapor, look at it. See, evaporation means this is our surface. Okay, the molecules will move from here to gaseous state. Okay, In summers, in I think in Haryana or Rajasthan, the phenomena can be observed very easily. That is, in summers, if you put an open basket full of water or an open bowl, then after some time, or maybe 4 to 5 hours, you see that the amount of water has decreased. Okay, so that is due to the concentration. The concentration difference results in the movement of molecules from the liquid surface to that in the atmosphere. Okay, it continues. If you keep the water open for many days in summers, then nearly the whole of the water gets evaporated. But in winters or during the rainy season, the water remains nearly same. Okay, so evaporation gets affected due to the temperature and pressure conditions or the humidity conditions of the atmosphere also. So you should check it out. That is, what are the conditions which are responsible for the change in evaporation rate. Okay, so think about the scenario. How will it change in the different conditions? Okay. Yeah, got the difference. Okay. um, so let's get to the next question. What is difference between gas and vapor? Now think about it and then tell me what is the difference. Air is a gas. It contains mixture, right? Yeah, you're right. Hmm. Vapor contains moisture, but gas doesn't. Okay. Air is a gas. It contains a little bit amount of water vapor also. Okay. See, but it's only in minimal amount, not in the considerable amount that it can be analyzed effectively. Okay. So yeah, all of you are right to the most. So I'll tell you the difference. I'll write down the difference here. Gas, vapor. Okay. Oh shit. Crap. Let me write it down again. I don't know what's happening with this system. I think the system is getting updated. So because of that, it is getting some problem. Okay. Gas and vapor. The gas, it can exist only in one thermodynamic phase. It can coexist with its vapor, as you have mentioned. Second, all gases are not vapors. It's like that we used to do in the school time, right? All vapors are gases. Okay. Um, a gas and does not change phase under normal conditions, but it can change phase under normal conditions. Okay. Hmm. Clear to everyone? These were some small differences between gas and vapor, which might be asked in some interviews because sometimes you know all the difficult concepts, but you forget the basic definitions, which get asked sometimes. Okay. Now, humidity. Okay. For humidification purpose, we'll use the sign convention, that is A. It will be used for water, and B means air. Okay, keep this thing in mind because the same notations will be used again and again in all the analysis that we'll do in the future for humidification. Okay, the humidity. Okay, first definition. I'm not. Am I visible to you? So it doesn't matter whether I am visible or not. And the only thing necessary is that you are able to listen to my voice and listen, see whatever it is written on the board. Okay, it's not so that you have to look at my face and then learn the things. So the first definition: absolute humidity will denote humidity with a cursive letter H in order to differentiate it from enthalpy, that is capital H. Okay, it is used for enthalpy. Capital H is used for humidity. Hmm. Absolute humidity is known as the kilogram of water vapor present in 1 kilogram of dry air. Okay, or it can also be termed as or the mass of water vapor carried by a unit mass of vapor free gas. Okay, this is the definition of absolute humidity. Because humidity concepts are more important for mechanical engineers and they deal with mass instead of moles, so the term absolute humidity is used in this way. So mathematically it is equal to what? H is equal to WA upon WB. That is, the WA is what? Mass of water. WB is the mass of air. Okay. Now W is equal to what? Na into Ma upon Nb into Mb, because number of moles is equal to what? Given weight upon molecular weight. Okay, that is equal to Ma over Mb into Na over Nb. Yeah, what is happening? Okay, so divide both numerator and denominator by total number of moles. We get what? Ma over Mb into Na over N upon Nb over N. Now number of moles divided by number of moles is equal to what? Ma over Mb into Ya over Yb. Okay, so multiply divided with pressure, we get what? Is equal to Ma over Mb into Pa over Pb is equal to Ma over Mb into Pa upon P minus Pa. A small pa is equal to what? Partial pressure of A. Small pb is equal to what? Partial pressure of B. So this is another formula for absolute humidity, where M is equal to mass of water vapor is equal to 18 molar mass, and Mb is equal to molar mass of air, which is equal to 29. Okay, so this is the formula. Any questions? अरे गजेंद्र जी यार चाय कहाँ है? चाय चाय. Any questions to anyone? No? Okay. So we'll use this relationship. Look at it. Humidity H is equal to MA by MB into YA upon YB. So is equal to what? MA upon MB into YA upon 1 minus YA. Okay. Now we will calculate the value of YA in terms of humidity, because sometimes the humidity is given to you and then you need to find out the mole fraction of that component into the gas phase. Okay. So it is calculated as follows. uh, Replace is equal to YY so that it becomes easy for us. So 1 upon H is equal to what? MB upon MA into 1 minus Y upon Y. Okay, this implies it is equal to MB upon MA into 1 by Y minus 1. Okay, this implies 1 by Y minus 1 is equal to what? It comes on the right hand side. It becomes reciprocal. MA upon MB into 1 by H. Okay, so it becomes equal to what? MA upon MB into H. This implies 1 by Y is equal to MA upon MB into H plus 1 is equal to MA plus MB into H upon MB into H. This implies Y is equal to MB into H upon MA plus MB into H. Okay, so got it. So divide both sides by denominator and numerator by MA MB. It becomes what? H over MA upon H over MA plus 1 upon MB. Got it? This relationship will be used further in deriving the expressions for adiabatic saturation temperature and the wet bulb temperature. In fact, in some vehicles also, this concept is used directly. Any questions? Okay. Let's get to the next definition, that is saturation humidity. Saturation means what? It is in equilibrium. Okay, so it is the humidity of air when water vapor is in equilibrium with liquid water at the given conditions of temperature and pressure. Okay, it means what? The pressure exerted by the water, that is water vapor, that is it becomes 100% saturated. Okay, so then it is called the saturation humidity, कि जितना प्रेशर हमारा वाटर लगाता है उतना ही प्रेशर हमारा वेपर लगाए. Okay, so it is again replace PA with PAS or PAV. Okay, so PAS is the saturation pressure, PAV is the vapor pressure, which is the same thing. Usually the saturation pressure is the term which is used for organic solvents, and vapor pressure is the term that is used for water, but both of them can be used interchangeably, they mean the same thing. Okay, so formula for HS becomes 18 upon 29 into PAS upon P minus PAS. Okay, the question. It's Delhi, right? There are a lot of mosquitoes around here. So this is called the saturation humidity. Now let's do the next. That is percentage humidity. Okay, it is what? The ratio of actual humidity to that of saturation humidity. Now when this is mentioned in this way, it is in the fraction or in terms of pressure percentage. In terms of percentage, it becomes what? H upon HS into 100. Okay, percentage humidity means ki how much the humidity is different from that of saturation value. Okay, so value of H is equal to PA upon P minus PA, and value of HS is equal to PAS upon P minus PAS. Okay, so it will become equal to what? PA upon PAS into P minus PAS upon P minus PA. Yeah, upon PA upon PAS into P minus PAS upon P minus PA. Okay, this is called the percentage saturation. Okay, 10-minute break for all of you people. Okay, just look at all the concepts that I've mentioned so far and try to do any questions that you can find. Okay, we'll meet again after 10 minutes. Welcome back, students. Everyone is present. Yeah. See, it's a difficult task to speak continuously for 3 to 4 hours, and for that, I need to take a little bit of break in between. And in fact, that is also needed for you people because things get a little bit drowsy if you keep on studying for a lot of time. So, in order to refresh your mind and the mood, 10-minute break is sufficient. Okay. So, everyone is again fresh for the studies. Yeah, let's continue. Hmm. We did the percentage humidity. Now, the percentage humidity can be expressed in two ways. The one is in terms of the percentage. The second one is in the terms of fraction. Okay. Now, the next concept is the relative humidity, HR. It is the ratio of partial pressure of vapor to the pressure of liquid at the gas temperature. Ratio of partial pressure of the vapor to the vapor pressure of the liquid at gas temperature. It is known as the relative humidity when expressed in terms of mole fraction or the fraction. Okay, in percentage, it will be equal to again Pa upon Pas into 100. Okay, there will be some questions based upon this concept, so you need to think clearly about it. Okay, now dew point. The temperature to which a vapor gas mixture must be cooled at constant humidity. You can't change humidity. You need to cool it without changing the humidity to become saturated. Saturated means what? That is, first drop of water is about to get formed. Okay, so this is known as the dew point. Similarly, what is the bubble point? The temperature to which a liquid mixture must be heated so that the first bubble or the first vapor, bunch of vapor is about to get formed. Okay, so this is known as the dew point. Similarly, when a liquid is about to vaporize, then it means it is called as the saturated liquid. It means it is about to change its form or phase. Okay, now humid heat. Humid heat. The amount of heat joule or kilojoule unit required to raise the temperature of 1 kilogram of humid air. Humid air means air plus water vapor by 1 Kelvin or 1 degree centigrade. It doesn't matter because both are the same thing. Okay, so this is known as the humid heat. So humid heat denoted by CS is equal to what? CPB plus CPA into H. CPB means what? The specific heat of air, which is 1.005 dry air per Kelvin. CPA is the specific enthalpy, specific heat of vapor, that is water, 1.88, and H is humidity. Okay, so at C in SI unit, CS is equal to 1.005 plus 1.88 into H. Important formula. Okay, the units are again kilojoule per kilogram dry air into Kelvin. Okay, this is known as the humid heat. Now, in terms of BTU or uh, FPS units, or known as the English units, it is equal to 0.24 plus 0.4 times 45 times of H. Units are in terms of BTU per pound of dry air into degree Fahrenheit. Okay, you need to remember only this formula: 1.005 plus 1.88 into H. Okay, yeah. Humid volume. It is the volume of what? Volume of 1 meter cube of humid air. Humid air means contains air as well as the water vapor. Okay, humid volume VH. The total volume of humid air, that is air plus water vapors at 1 atmospheric pressure, and the gas temperature. Okay, for an ideal gas, it will come out to be VH is equal to 22.414 upon 273 into T, because value of 22.4.4 is at 273, plus 1 upon 29 plus H upon 18. The units are again meter cube per kilogram of dry air. C, 22.414 is what? The molar volume at STP. So this is to account for the volume, then into temperature, because PV is equal to nRT. Okay, the volumes is direct proportional to T. So that's why direct proportional means here inverse proportional to temperature or for this, okay, or V1 over V2 is equal to T1 upon T2. This plus V2 is equal to V1 by T1 into T2. So we have done that. That molar volume is equal to 2.44 273 into T2. Same thing. Okay. So since we needed the absolute values, we have done this thing. Okay. Humidity means what? The amount of water present inside the mixture. So H upon 18. Like we have done in what? The formula for YA, which was what? YA is equal to H upon MA upon 1 by MB plus H upon MA. Okay. So it's the same thing. Okay. So for in FPS units, it will come out to be VH is equal to 359 upon 492 अरे यार into T. What is happening? 1 upon MB plus H upon MA. Okay. NFS units feet cube upon LPM dry air. Okay. So any questions? Yeah. Now we'll calculate the total enthalpy. So enthalpy will contain first the concept of what? The specific as well as the latent. Okay, since the specific or enthalpy is related to what? Temperature change, and the latent enthalpy is related to the phase change. Okay, so total enthalpy will be equal to the sum of both. The enthalpy of unit mass of humid air, that is air plus vapor. Okay, so Hy is equal to Cs into T minus T naught, that is the specific enthalpy, plus H into lambda naught, because only the moisture will change the phase, air will not change the phase. So we'll need to consider only the latent heat of vaporization or condensation. This is the same thing, only change in sign for into the humidity. Okay, so this is latent heat. So or the sensible heat, this is known as specific or sensible heat. Okay, so value will become what? Cs was written as 1.005 plus 1.88 into H into T minus T naught plus H into lambda naught. Okay, now if the 0 degree centigrade or the standard temperature is considered as the reference temperature, if STP is the reference point, then the value of Hy will become 1.005 plus 1.88 into H into, we can take either Kelvin or degree centigrade, it doesn't matter because we are differentiating the two things, plus 2501.4, or it is sometimes written as 2500. Okay, so units are again kilojoule per kilogram dry air. Okay, any questions? Anyone else? Any problem? Let's do some questions. We have done a lot of concepts. It will be better thing to do the question right now because the other derivation is a little bit of difficult. Yeah. Okay. Let's go to. Let me check out the page number. I'll tell you where you can find this question. It is a GATE 2007 question. Yeah. The question number 68. Okay. That is, if the percentage humidity of air is this, and saturation pressure of water vapor at the temperature is this, the percentage relative humidity and absolute humidity of air are what? Got the question? The page number 139. The question number 68. Got it? Okay, do this question. Answer. Tell me the answer. Which option? Do it total and then tell me the answer. Okay. Yeah. A is the correct answer. Everyone else got it? Yes, students. Mr. Abhay, Miss Swati, Mr. Ahmed, what happened? You haven't done it. It's GATE 2007 question, yaar. Question number 68. Okay. So everyone got it, the answer? Got the answer? That is A. It's a simple problem. Right? The answer is A. Yeah. Okay. Let's move on to the next derivation, that is adiabatic saturation temperature. Okay. It is the, just look carefully at the definitions that I'll mention for adiabatic saturation temperature as well as the wet bulb temperature, because the definition in itself clears a lot of things. Okay. It is the temperature of the air or gas in contact with a large amount of water in an adiabatic chamber. Okay, let's make the diagram. This is the chamber. This is your pump. Let's take water with blue. Okay, so this is not blue. I have a little problem with colors. Just tell me, is it blue or not? Uh, is it blue? Right? I think it's a little bit gray. Not blue. Which one is blue here? No, not this. No, let's take this one as the blue one. Okay. See, I'm a little bit of colorblind. See, I can see the colors, but I can't differentiate between those colors because for me, all the three shades that I use are for blue. Okay, so it's usually a forte of girls, so they might be knowing whether it's blue or not. So let's take that. This is water. Uh, it will get inside pump, so it will be pumped back into the system from here. Okay, we have installed a sprayer like that of your fountain. Okay, the apparatus that you use to bath in the bathroom, similar to that. Okay, fountain like structure or whatever you call it. Okay, so let this is the hair. This is your water, and so during the process a little bit of water will get used up, so we apply makeup water. Makeup water means the water which is used to make up, means to fulfill the requirements, not the makeup that we apply on the face. उस makeup की बात नहीं कर रहा हूँ मैं, that girls apply. I'm talking about the makeup water, that is, and while we do the operation, a little bit amount of water gets moved on from liquid state to the gaseous state. Okay, so in order to um, in order to take care of that shortage of water, we apply some fresh water known as the makeup water. So it is at the temperature of saturation temperature Ts. Okay. Hmm. And let the gas be with green. Okay. Yeah, this is green. So this is inlet gas at temperature of T and at a humidity of H. Okay, so this gas will be in contact with a lot of water which is being sprayed through these nozzles, or you can say sprayer or fountain, whatever you say, and that changes the humidity and temperature of the gas. Humidity becomes Hs and temperature becomes Ts. Okay, the overall this chamber is insulated so that we don't consider any heat loss from here. We consider it as the ideal case. Otherwise, we will have to take care of heat effects also. So in order to simplify the case, we consider that this chamber is full insulated. The only interactions that are occurring for heat are within this air and the water. Okay, so the whole process is adiabatic in nature and a steady state process in which the air is in contact with a large amount of water. So water is continuously pumped up, and if some amount is reduced, then it is given as a fresh feed. Okay, in order to make up with that, it is in water. Okay, huh. Now some notes to mention about it. Note. Now, if gas is entering at temperature T and humidity H, then obviously T will be greater than Ts. That is, on contacting with air, the temperature will get reduced. Like that in your desert cooler, the cooler that you use in summers, it gives you an air that has a temperature lower than that of the atmospheric temperature. Okay, that's because of the same concept, that is the adiabatic saturation temperature, which exists because the similar kind of phenomena occurs inside it also. The water keeps on pouring down the, uh, the sideways, and the air keeps on passing through it. Okay, like that in this case. And so the temperature, okay, and humidity will be obviously less than that of atmospheric humidity, the saturation humidity, that is H is less than HS, because the air that desert cooler emits is usually the humid air, and the air that was already present into the atmosphere is the dry air. Okay. Hmm. uh, if the contact time between air and water is very large, then it allows equilibrium to be get attained, and then in that condition the temperature will become equal to the saturation temperature and humidity becomes equal to the saturation humidity. But if the contact time is not so, then temperature will be greater than Ts. Okay, the final temperature, the equivalent to the saturation temperature, will not be achieved. The cooling will be less. Okay, and similarly the humidity will be less than the saturation humidity. Okay, the percentage value won't be 100%, it will be a little bit less than that, but the humidity will increase and temperature will decrease. That is sure to happen. Okay, and the assumptions. Number one, pump work is neglected. Neglected, yeah, the work is neglected. So we don't need to calculate what is the pump work. That is the fluid mechanics problem, and why to complicate things when you can simplify the things and get the temperature. The second one is that enthalpy of makeup liquid is zero. What does this mean? It means that we assume that whatever the temperature water we are applying as a makeup water, it has the temperature the same as that of the adiabatic saturation temperature. Why? Because the temperature will be more than that. Then first that water needs to get cooled down, and then it will change its form. That is, then the evaporation will occur, or the vaporization will occur. Okay. So if the water is too cold, then it will decrease the temperature of air as well as the water present inside the system. Okay. So we need to consider the enthalpy effects if we consider the enthalpy of makeup liquid not equal to zero. जैसे कि you must have observed that if you feed hot water inside the cool desert cooler, then the air that it will expel out will be a little bit of hotter than that in the case of a normal water. Similarly, if the water that you have put inside the cooler is chilled one, that is, it contains ice, and then you apply, then you start the cooler, then obviously you'll get a lot of cold air. Okay, so that's the same thing. Now let's do the derivation. Any questions up to this point? Ask me any questions if there are any questions. Okay, so the derivation, let's do it. Yeah, the yeah, saturation. First, shall we do the derivation, and then I'll tell the whole concept of saturation in detail. Yeah. So it's good thing that you asked me, but you should have asked sooner when I mentioned the dew point and all those things, and there I mentioned the saturation. Okay, so be a little bit attentive. Ask on the spot. Okay, so because then I'll be able to correlate with the terms that I have mentioned at that point. Okay, be a little bit more attentive. It's good thing that you asked me this question. In fact, all of you should ask questions from me. Only then I'll come to know whether you are understanding the things or there are some problems or not. Okay, if you won't ask me questions, then I'll just assume that whatever has been taught to you is well understood to everyone, and there is no problem regarding it. Okay, so let's ask questions now. Considering Ts, that is saturation temperature, as the datum. Datum means the reference point. Okay, the point from where we are doing the calculations is known as the reference point or the datum. Okay, so the total, the mosquitoes, a lot of mosquitoes here. Yeah, so the total enthalpy balance is what? The enthalpy of entering gas is equal to enthalpy of leaving gas. Okay, that is Cs into T minus Ts plus H into lambda S is equal to Cs into the, for the exit gas temperature is equal to the saturation temperature plus humidity will increase. It will become to the saturation humidity. That is, initially it was what? Total enthalpy, which is equal to the sensible heat plus latent heat. Okay, then final also the sensible heat plus latent heat. But since the temperature is equal to the datum temperature, it will become equal to the 0. Okay, so this implies Cs into T minus Ts is equal to Hs lambda s minus H into lambda s, or Cs into T minus Ts. I sprayed too much of it. Is equal to Hs minus H into lambda S. Okay, so Cs upon lambda S is equal to what? Hs minus H upon T minus Ts is equal to, so in terms of simple terms, or Hs minus H upon Ts minus T is equal to minus Cs upon lambda S. Okay, so this is the characteristic equation that is used to find out the adiabatic saturation temperature. Okay, what is the value of, or you can write H minus Hs upon T minus Ts is equal to minus Cs upon lambda S. Okay, so value of Cs is equal to what? 1.005 plus 1.88 into H. So this is the equation of adiabatic saturation curve passing through Hs, Ts and H, T. Okay, so this is the characteristic equation line for a adiabatic saturation curve. Okay, any problem in the derivation? Yeah, anyone else? Any problem? This is simple derivation, right? Any questions? Students? Okay. I shall move forward on explaining the saturation, right? Yeah, saturation. Before explaining this concept, just tell me, uh, what does saturation means to you in general terms? According to you, what should be the definition of saturation? Look, मतलब क्या होता है saturation according to you people? Any guess? Hmm? According to you people, what should be the definition or the meaning of saturation? Yeah, a sort of yeah, means whatever the thing is happening, whatever the thing is presented, it is on the verge of change. Some change is about to be felt into the system, right? Something is about to get changed. Like while mixing, saturation means if we pour a more amount of solid inside it, then the solid will get separated out, right? Similarly, if we heat up a such thing and it is about to become saturated, it means it is about to change the phase. Similarly, if we cool a vapor at saturation point, it is about to change again. Okay, so term saturation refers to the point, means a specific value of the set of properties such as concentration or mass fraction, mole fraction, temperature, pressure, etc. Okay, a point is reached in such a way that the system is about to go a change, usually a change in phase. Okay, so this is known as saturation, means अति हो गई है किसी चीज की. For example, if you are studying continuously for a long period of time and then you get saturated, it means your mind won't be able to get a more amount of knowledge from it, from that from whatever thing you are reading. Similarly, um, if you are handling a thing that someone is abusing you, and then you are just expressing your anger, so on, so on, so on, and at the point it becomes saturated that you become so frustrated that you are about to get angry. Okay, it means that is the saturation limit. Similarly, this is the case of saturation for the systems also. Okay, ऐसा होता है ना, sometimes it happens that you want to say something very bad rude to someone but you just uh, handles yourself. Okay, yeah. So this is called the saturation in the say in the specific terms also. Yeah, it is related to the equilibrium, that is at the saturation point there is an attainment of equilibrium, and after that a change will be occurred. Okay, in a way you can say that it's about to get changed, the equilibrium is about to get disturbed, or it might get attained. Both things can happen. Okay, I'll tell you how it gets changed. Yeah, let's say a saturated vapor. Okay, first let's have a vapor. Vapor means it contains water. Let's consider water vapor into the atmosphere. So you started cooling it down. You started to cooling. So the temperature will keep on decreasing, but humidity will remain constant. Okay, so on decreasing the temperature, the water vapor present inside the air, we also get cool down. Okay, let it at atmospheric conditions. So when it will reach 100 degrees centigrade, then what will happen? The vapors, fraction of vapors will about to get condensed. Okay, that is, it is on the verge of condensation. Okay, so it means what? At this point, that air or the gas mixture is handling or holding the maximum amount of vapor that it can contain. Okay, now on further decreasing the temperature, what will happen? H will get reduced because the air will lose some water. Okay, so yeah, the humidity has changed. Now, how it is related with equilibrium? Voice is not clear. I think there is some attenuation in the background, so because of that, it might be possible. Is it clear now? Let me place the mouthpiece near to my mouth. Yeah, is it clear now, Swati? Yeah, okay. So, on cooling down the temperature, the humidity will remain constant, but the temperature will keep on decreasing until the point is reached at which the temperature will become equal to its condensation temperature. That is, for atmospheric conditions for water, it is 100 degrees centigrade. Okay, so attainment of this temperature will cause what? The humidity to be on its verge of changing. So on further decreasing the temperature, the humidity will get reduced because the water will be condensed out of the system. Okay, see, Mr. Abhay, every mass transfer process is associated with the system wanting to achieve equilibrium. Okay, it means what? See, humidification and drying or evaporation occurs simultaneously. Right now, I'm telling you only a portion or only a portion, okay, that is related to humidification. Okay, so these equilibrium questions should be asked after the chapter is completed or the syllabus is completed. Okay, see, I'll answer these questions in the future lectures. If I'll tell you everything that is happening at the same point, then none of you will be able to understand the things. Okay, so I'm telling a fraction that is related only to humidity at a point. Then I'll tell you a fraction that is related only to drying, and then I'll merge both the concepts and tell you how the equilibrium is attained. Okay, how the mass transfer is occurring so that there is an attainment of equilibrium in the system. Okay, so don't put up the question of equilibrium time and again, because I'll explain it to you in the time being. So don't get wrong feeling. Okay, it's that if you will relate the question of equilibrium to each and every case, then I'll have to repeat each and every thing again and again. Okay, so I'll tell you everything, so be a little bit patient. Okay. Yeah. So similarly, saturated liquid. Let a liquid is present inside it, and we started to heat it up. So the temperature will keep on increasing, okay, until a point is reached. See, on heating it, what will happen? A fraction of liquid will get changed into vapors, but it won't be able to leave this bulk very easily because there is an atmospheric pressure acting above it, which is uh, not allowing these vapors to get escape from the liquid state. So at saturated point, what will happen? The pressure or vapor pressure will be converted to the atmospheric pressure that is happening inside it. Yeah, no worries. I think there is some technical error. Everyone else is listening to me? Yeah, I think there is some network issue because the video is clear to me. So I think there is some network issue. But see, it is the same thing. The concept that I mentioned for the vapor is the similarly the concept that I'm mentioning for the saturated liquid also. Okay? Okay. Just look at the board. Similar to the case of saturated vapor. Okay? On heating a liquid, the temperature will keep on keep on increasing until a point is reached in such a way that at this point the vapor pressure is equal to the pressure above it. Okay. Okay. So on increasing on increasing the temperature even more, the phase change from liquid to vapor phase will take place. Okay, got it? Yeah. Any question? Okay. See, there seems to be some technical problems. I'll try to get them fixed tomorrow in daytime. Okay, so we will stop here as of now. Practice the questions related to the concepts taught so far. Okay, books, travel, BK Datta, GN Complex. Okay, practice it. Yeah, good night. Okay.